Let's continue in 4.7, 14.7. I almost messed it up again. So next example, another application type question. This one says, for a fixed sum, A, B, C, A plus B plus C, and those are going to be the sides. Show that, or the axes, show that the ellipsoid of maximum volume is a sphere. In other words, those are equal. So you have some ellipsoid, and so we'll first write down the formula for ellipsoid. So we have an ellipsoid is this form: x squared over a squared, y squared over b squared, z squared over c squared equal to 1. That's the formula for an ellipsoid. And then you have the volume of a ellipsoid. This one you could look up, but it's 4 pi times a times b times c over 3. Or you could write it as 4 pi thirds. So remember, a sphere is 4 thirds pi r cubed. Well, this is just, you multiply the sides, a, b, c. So what are we going to use? I mean, those are formulas we have. We talked about this is the formula of an ellipsoid. We have a fixed sum, meaning it's equal to a constant, say k. And then we have a volume formula. So what are we trying to minimize or maximize? So we're trying to maximize volume. So that's what we see. That's what we're going to use. So we want to maximize volume. So that means we need to find the maximum value of this function. Okay, of this function. This is what we want to maximize. So maximize isn't really a word, but just it sounds good. So we want to, I mean, meaning, it's a word, it's just not really meaning here, but maximize v of x, y, z. Well, that's ABC. And that's where I wrote this down, ABC, on purpose, because I want you to see that it's right now a function of 3 variables. How are we going to get this a function of 2 variables? Okay, well, that has to do with, of course, the ABC. All right, so let's look at the solution to this. Okay, so here's our solution. I don't always write down solution, but I did this time. Okay, so let A plus B plus C equal to a constant be fixed. Okay, and then we're going to solve for C. It doesn't matter which one. Just got to get one of the variables in terms of the other. So C is equal to K minus A minus B. Then we're going to substitute. Then substitute into V. So we're going to have volume in terms of just A and B. And K is fixed. It's a constant. It's like 5 or something like that. Okay, so now we can write the volume V of AB in terms of those 2 variables. We're going to substitute for C. So we have 4 pi thirds times A times B times K minus A minus B, which is equal to 4 pi thirds. And then we can distribute. So we get KAB minus A squared B minus AB squared. Okay, and then, so what's next? We have our function now in terms of just A and B. Now we want to find our critical points. So find the critical points, you do the partials. So we're going to do the partial of v with respect to a. Okay, so you're going to take this partial with respect to a and then go back with respect to b. So v with respect to a is 4 pi thirds. And then do our calculation. So it's kb minus 2ab minus b squared. We're going to set that equal to 0. And then do partial of v with respect to b. So it's 4 pi thirds. It's ka minus a squared minus 2ab equal to 0. So we can divide out the 4 pi thirds. That's gone, of course. Okay, so we get, let's see, where am I at here? So we divide that out, and we get kb minus 2ab minus b squared equal to 0. And we get ka minus a squared minus 2ab equal to 0. Okay, so there's my system that we want to solve. So we can, let's see, we can factor out a b. So we have b, and then k minus 2a minus b. And then we can factor out an a. We have k minus a minus 2b. All right, so for that, right now, we could say there's, well, no, it's equal to 0, sorry. Equal to 0, equal to 0. So right now, a equal to b equal to 0 is a critical point, because that's this solution right here. So you basically set each equal to 0 and solve. Okay, but that's not going to get us anywhere. So you have a critical point of 0, 0. And of course, we omit that. We omit, since we are assuming both A and B, well, and C are all positive, right? Because they're lengths, they have to be a length. All right, so we're going to do that in a different way. So we can solve for k. So we can say k is equal to 2a plus b. And then we can substitute back into the second one, into 2. So we could call this 1 and this 2 if we want. And then we can have, at least in terms of 2 variables. Okay, so substitute back into 2, and we get, let's see, 2a plus b minus a minus 2b equal to 0. And we're just substituting into here. Right, we're ignoring, so it's k is 2a plus b, and then minus a minus 2b. So that's all I did right here. Here's your k minus that. And then we can simplify that a bit. And we get a minus b equal to 0. Okay, well that's equivalent to just a equals b. All right, so basically you're getting a equals b. That means you can substitute and find out what k is in terms of a and b. Okay, so we can substitute into either equation above. Let me write out what I'm doing to isolate in terms of k. So we have k minus 2a. Now we can say minus a equal to 0. All right, and then you can solve for a. Okay, so you have k minus 3a equal to 0, or a is equal to k over 3. So a is k over 3, which is equal to b. Okay, now what does that mean for c? Well, if we have a plus b plus c equal to k, all right, then and then a and b are k thirds, that means c has to be k thirds. So you basically have k thirds plus k thirds plus c equal to k. Okay, so if you solve that, you can, I mean, it's pretty clear now that c has to be k thirds. It's like the 1/3, 1/3, 1/3. You could actually, without loss of generality, is what they say. That's a nice fancy word of saying. You could actually make this a 1, and it wouldn't matter, because it's still just an arbitrary value that you're throwing in, and it's just a relationship of the sides. So you'd end up getting 1/3, 1/3, 1/3. But didn't say that, so I wanted to keep it as just k. So, so that basically shows that they're all the same. Therefore, a equals b equals c. So I'm going to show you two ways to argue this. So this is the only critical point. Therefore, it must be maximum. So if it's the only critical point, it must be a maximum and is a sphere. So in other words, you're getting one critical point. Well, it can't be a minimum, because you could have like this really skinny ellipsoid with almost zero volume to it. Right, so you could stretch that out infinitely, really, like forever, not forever, but just, and you have this tiny ellipsoid and smash the volume to nothing. So it wouldn't make sense for it to be a minimum, in other words. That's really the argument. So we know it is. Now you can actually show this by the second partials test. So we can show this is maximum by the second partials test. Okay. So I'll throw that up so you can try it. Okay, and I'll give you one more example. I'm going to paste everything down here, and then you'll have a couple to work with. So let's just do that. We've done enough in this section. So a lot of practice to do on your own. Let me go and grab those other questions over here. That's the ellipsoid question. So here's the second partials test. How you can demonstrate that. Okay, so try that one. See if this makes sense. Okay, and then I'll just do another example down there, and then we'll do this other example. So you can try this example on your own. And then I guess I'll leave those off. So this is just a little more sophisticated question. Not sure it fits right there. Oh, it does. We'll just put it right there. Barely. Okay. So try this one. And then so you can do the second partial test and then try this one. Find the local maximum minimum saddle points of this function right here. Okay, so you can distribute. So this is the function that you're minimizing, maximizing. Then you apply the second partials test. So here's the rest of it. So you can try that on your own. I've done already a number of these, and then we'll go into the next concept. Okay, so check that one out. And then there's the second partials test. You can see everything works out. Not obvious stuff on that one. But the nice thing about this section is I'm not going to deviate from the process of the second partials test. Something will be very similar to all this. You just got to be able to apply it and get the right form and make a little argument at the end, right? You got to say stuff like this and is local max because of, where is it? Because your discriminant does something. So you got to describe what the discriminant does and then that. All right, so you got to do that kind of stuff. Be a bit organized. Otherwise, that's it. We have one more section to go, and we're done with chapter 14.